me. Oh, shucks. What? Did I make a mistake? No, it feels like I'm good too. Feels like though you don't have enough. You do have enough. Okay? Because this took me 10 seconds and this also works, but is going to be a gob over. So I was just trying to save you some time, but if you say no, no, I want to do the work. I want to work foolisher, but not smarter. Foolisher is a word. Are you ready? Okay. Now, if you use the 0.11, that allows you to find y initial, yay? And so what is y initial? 1 over e squared. You agree? You don't agree? Why don't you agree? Why don't you know? What's the problem? Is it just me here? Are you have somebody with me? Yeah. Okay. Let's go back there. Because if I'm losing top students, all right. It would be one thing if I was losing always confused students, but if I'm losing top students, that's bad. All right. So here we go. First of all, I know we just talked about this yesterday, but that's a really famous differential equation. And if you recognize it, you'll be able to save yourself some time. And in fact, sometimes it won't even be possible otherwise if you don't. So we need to understand that a constant times the dependent variable, y, is the differential equation for exponential growth. You should then, rather than do all the separation of variables, start from the differential equation, or from the exponential growth equation, but using the variables they give you. So it shouldn't be a here, because there's no a in this problem. It should be y. Are you with me now? Okay? Now, if this is typically the k, then instead of a naught e to the kt, I'm going to go y naught e to the 2t, because k is 2. Okay? Now, to find y naught, you need an initial condition to do that, and that's where I'm using 1, 1. So if I plug in 1 for x, 1 for t, should be not 2t, it should be 2x here, shouldn't it? Sorry, maybe that's why you're confused. Why are you using t? It should have been t, it should be x. Okay, so if I plug in 1 and solve, I get 1 equals y times y initial times e squared, yay? So y initial is 1 over e squared, and my equation is y equals 1 over e squared e to the 2x. Say you're doing a multiple choice and you don't see that answer. What's another possible form of that? E to the 2x minus 2, perhaps you would see. All right? Yes? Yes, so here, did you plug in the initial condition here? Yes, you did, because you want to use the initial condition as soon as possible. If you do that, actually, let me go back here. Sorry, Isabel, did you move the 2 over with the y, or did you leave it on the dx side? Moved over with the y? Okay, so this is your differential equation, this is your antiderivative, and now I'm using the initial condition to find the c. Are we cool? Okay, log of 1 is 0, so that means c is negative 1. If I plug c of negative 1 back in, I have 1/2 log of absolute value of y equals x minus 1. Cool? If I then dump the 1/2, then log of y equals 2x minus 2. If I dump the log, y absolute value is e to the 2x minus 2. And then y is plus or minus. When you dump absolute value, it's plus or minus. But given that the curve passes through 1, 1, it must be the case that y is positive. And so we choose the positive, our equation is e to the 2x minus 2. Does that make sense? Okay. You should be able to do both, but in terms of time, you want to recognize. All right, today's lesson is a humdinger. It's a beauty. It's wonderful, and it's very important. You'll love it. Are you ready? Okay. Now, some of you were probably really good with arithmetic when you were in grade school. Yeah, you had what is commonly called good number sense. Some of you only learned math through discipline and hard work, but it doesn't just, oh, that makes sense, I'll come easy to you. Now, in terms of number sense here, some of you with great number sense might be able to look at those numbers and tell me the average. The average is? What? 90. Who says? How did you do that? I assume you didn't just add all those numbers and divide by 5 just like that. What did you do?
Like 88 and 92 are both away from 90 and then 84.
Beautiful. Okay. So what he just did, that mental math, is mental averaging. That's how you could, a person with good number sense could look at a whole class set of numbers and average them mentally just by looking at differences from what the mean would expect. He looked at these and said, well, look at those two. Those kind of cancel each other out. 88 is 2 below 90, 92 is 2 above 90, so it feels like those kind of work out to be 90. Same with this. Isn't this 6 below 90 and that's 6 above 90? So they kind of cancel each other out. 90, 90, 90, 90. He's absolutely right. The average is 90. Now, graphically, if you were to do this, think of it this way with the break in the scale here. 84, 86, 88, 90. The visual is helpful to understand the lesson of the day. All right? So, if I were to mark each of those tests, 88 is here. 92 is here. 84 is here. 96 is there. And 90 is here. You with me? Now, all that stuff that he did mentally, he said, I feel like the average is in the middle, and of course, that's true. But look at, in terms of distances above and below. This is 2 below, and this is 2 above. So they kind of cancel each other out, yeah? And 6 below and 6 above. Those kind of cancel each other out, and that's right on the average. Now, remember that idea in just a minute when we talk calculus, because in calculus, you don't average one number or 2 numbers or 5 numbers. You average infinitely many numbers. You can add and average infinitely many numbers with calculus. So let's go here. This curve, y equals x squared, has infinitely many values, yeah? From -3 to 3. What's the average y value? Ballpark. What is it? Just take a guess. I mean, if I were to draw the average value, wouldn't it be somewhere between the max and the min, yeah? So maybe about, I don't know, 5? A little more. Like this, yeah? All right. So we're saying that f at c, which stands for the average value, is about 5 1/4. Right? All right. Here's the average value, by the way. Maybe we'll find that in just a second. All right. Now, in terms of what we just talked about, in some cases the square is going to be above that average value here, and in some cases the average value is going to be below, above and below, right? But if that's truly the perfect average, then those above and below areas should knock each other out. They should cancel each other. Net zero change, yeah? Areas should cancel. follow? The black area versus the green area. So, would you do that same thing for the next two? Just try and draw where the average y value is, and then just estimate what you think f at c, or the average y value would be. Obviously, there's no right or wrong unless you're really dumb and you say something beyond the region itself, which is ridiculous. Okay. So just take a stab at it. It's an estimate. You're trying to draw a line, though, where the area above and below is about comparable. Oh, by the way, this is -1 here, the min. Sorry about that. I forgot to mark that in before I copied it. How we doing? You have something comparable to what I'm talking about for the second one. My average value is in here somewhere, and I say, it's about a y value of 2. Yeah? And the next one, the y value or average y value is in here somewhere, and I figure about -1/2. Cool? All right, now we're going to do the same thing except one more step here. On these, I want you to do two things. I want you to estimate the average y value and then also estimate the average x value, or the x value where that occurs. Let's do one together. So here, this is going from 2 to 8. So it seems logical because it's linear. The average value would be somewhere halfway between 2 and 8. So 5. Yes? F at C. So I am saying that F at C is 5, and I'm actually going to go hard and because I'm pretty doggone sure that the average value is 5. Right? Now I also want you to tell me that's F at C. In other words, the average y value. The C stands for the x at which the average value is made. What does it seem like the average value is made at? A C of 3? I know my picture's a little clearer, but it feels like C is 3, okay? F at C is the average y value. C represents the x at which the average value is made. Do you understand what I'm looking at? Okay, do it on the other two, please. Don't worry about the axis here. You're talking about the distance between the average value and the curve, so ignore the axis. An estimate, yours might not totally agree. Yeah? Okay, last one. What's this didn't turn out well, but this is the bar here. Just there. So what's the average y value there? Where did you throw your average value? Right, in here? Okay, so F at C, and that is, assuming the scale is 1, this F at C looks like 1.5? Isn't it 1.5? Here's 1, here's 2, here's 3. So I feel like 1.5, right? Okay, now what about the C at which that's made? Where's the point on the curve where that's made? So your silence is correct. C, there isn't one. Why do you reckon that is? How come there isn't a place where the average value is made? Yeah, it's not continuous. So that's called the mean value theorem for integrals. We'll talk about that in a second. But let's go to the theory, all right? So rather than visually estimating the average value, let's figure out an actual way to calculate the average value exactly. How do you find the average value exactly? That's the question of the day. Second question is, how do you find the x that makes that average value? We'll come to that second. That's the second part of it. All right. If you were to sketch y equals 1 plus sine of x, I think you'll agree that the amplitude is 1 and the center line is 1. And if we just graph on one period from 0 to 2 pi, that'll be fine. Okay? You check? You with me? All right. Now this one's nice because the average value is pretty easy to locate. What's the average value? 1. And that's because the area above and the area below knock each other out. Lee? All right. Now, here's where we are going to come up with the actual formula. Would you take this, and we're going to split it into two graphs. One is the sinusoid and the area beneath it. The area beneath the sinusoid looks like that, yeah? And now, would you graph next to it the graph of the green rectangle that ends at 2 pi. So if you were to draw that rectangle of area beneath the average value to 2 pi. Now I have a point here. What is the relationship between those areas? They're the same, okay? If I took this little overage here and flipped it over and filled that underage there, wouldn't they have exactly the same area, right? Are you with me? All right. Now, how can we use this to find f at c? Well, let's go to the area under the sine curve and the area under the green rectangle. How would you find the area under that sine curve? Integrate from 0 to 2 pi of sine of x, and that would give me the area. Now what about the green rectangle? What's the base? 2 pi. Would you write 2 pi minus 0? Just because. And what's the height? F at c. The height is the average value we're looking for. Now if we solve for the average value, because that is the question, what is that average value, then isn't the average value equal to 1 over 2 pi minus 0, or dividing over the base of the rectangle times the integral? There. Now we kind of know visually that that should be 1. Right? We already kind of know that the average value should be 1. But let's check it out and verify. what is the antiderivative of sine? Cosine or negative cosine? Negative cosine from 0 to 2 pi, 1 over 2 pi. Negative cosine of 2 pi. This is not coming out what I want it to be. Oh, that's why, phew, I was starting to freak out. I thought calculus was broken. All right, so the function is 1 plus sine of x. Thank you. 1 plus sine of x. I did not, in fact, break calculus. Thank goodness. All right, let's go back here. What's the antiderivative now? X minus cosine of x. Phew. All right, at 2 pi then, I'd get 2 pi minus cosine of 2 pi. And then I'd subtract 0 minus cosine of 0. Oui, oui. All right. 2 pi is 2 pi. What's cosine of 2 pi? 1. Cosine of 0 is 1, and because it's minus negative, that's plus 1. The 1's drop away. 2 pi divided by pi is, 2 divided by 2 pi is 1. So surely enough, it verifies. Now, then, this idea, that's how you find average value. And the idea comes from the fact that the areas of the actual area under the curve and the area made by the average value rectangle should be the same. And if you then want to focus on that average value, you're really dividing the base of that rectangle over. So this average value comes from finding the area under the curve and dividing over the base to isolate just the height of that rectangle. Are you with me? So this then is the formula for average value. To find the average value of a function, you take 1 over the region width and divide it into the integral area, or the area of the integral, or the area of the, under the curve, and you're good to go. So let's do 1 for practice, and then we'll go on to part 2. So if I gave you, find the average value of this baby, would you try that on your own, please? And then we'll talk about it. You should not need a calculator. You should be able to do this without a calculator. Don't worry about it. It's ugly. I got something like 2 over pi times the sum 3 pi squared over 8 plus 1. Is that what you have? Okay. Now, that was the first thing we did. Find the average value. What's the average y value? Okay. Surely, it's hard to check, but if you were to put this into your calculator, what should it most definitely be between? Actually, it wouldn't be in here. It would be somewhere in the region of the curve, right? It would have to be between the min and the max of the curve itself. You couldn't have an average beyond the scope of the numbers, right? All right. Now let's go to this part. Unfortunately named mean value theorem for integrals. And right away, students get this one and the mean value theorem, which is to say for derivatives, confused. So mean value theorem for integrals, focus on the mean. It's the average value theorem for integrals, and it basically says something like this. if the function is continuous, there has to be a C in the interval where the average value is made. Now that theorem looks pretty intimidating. Let's go back here to this picture and I'll clarify here. Here, it had an average value and there actually was a point where the average value was made, yeah? There was a C where the average value actually occurs on the curve. Here, there was an average value and there was a C where the average value was made. There is a point on the curve. Now it's because those were continuous. They went continuously from their low to their high, so they had to pass through the average value in between. But if you get something that's not continuous, there is no place on this graph where the average value is made here. In this case, the mean value theorem for integrals fails. There isn't a place on the curve where the average value occurs because it doesn't go from its low to its high continuously. It's choppy. And so there is no x value to be found where the average occurs. So now, a problem that you're going to be faced with is not just sometimes find the average value. If they say find the average value, then you're just finding the y value, circling it, done. But if they say find the c guaranteed by the mean value theorem for integrals, then you are finding the x value where the average value is made. Okay, and that is, in essence, the mean value theorem for integrals is if a function is continuous, there must be an x or an x equals c that makes the average value. Okay, so if the problem reads like this, then this is the process. Instead of working just the left side, you're actually going to be finding the average value on the right side, and then also working a little on the left. So your goal is to take f of c equals 1 over 2 minus 1 from 1 to 2 of 2 plus x cubed dx, and you need to find c. Your end goal is c is this. All right? Now, it's up to you if you work both sides at a time or you first find the average value, kind of like I taught you on mean value theorem for derivatives, and then later do the c part. Do you want to do both sides together or find the average value first and then do the c part? All right, so we'll find the average value first part. Average value. Okay? If I find the average value, then the fraction, thankfully, comes out to be 1. What's the antiderivative? 2x plus x to the 4th over 4, or 1/4 x to the 4th, I heard, from 1 to 2. Yes? Stop me if you have a question or if I said something incorrect. F at c, then, is 4 plus 16 fourths when I evaluate at 2, minus 2 plus 1/4 when I evaluate at 1. So f at c is 2 plus 15 fourths. And so f at c is, what, 19 fourths? Nope, 23 fourths, right? Do you concur? All right. Now, that's great, but now I actually have to find the c. The curve is 2 plus x cubed. So f at c is 2 plus c cubed is 23 fourths. That means c cubed is 15 fourths. And so c is the square root of 15. No, the cube root of 15 fourths. All right. And that is in the interval, by the way, the cube root of whatever that is, 3-ish, is in between 1 and 2. All right? You tracking? Okay. Would you use your calculator to find this answer, please? You may use your calculator. Go. one is from an AP test. I just want you to make sure you can answer AP style questions. You do some paper and pencil work before you're ready to pick up the calculator. Sure you do.
Alright, I need to get my calculator out. Seven plus Actually, am I even ready for this? I'm not ready for this. I should get my act together first. You did that for right. That makes sense. 7.547.
Okay. Okay. You about with me there? So far, so good? Okay. Tempting to find at that answer right now. This is very common in the AP test. They'll have intermediate answers. I think I've talked about this already. They'll have answers along the way as multiple choices. And if you're rushing, say, oh, there's the answer right there, I'm done. No, you're not done. That's the average value. But does the question say, what is the average value? No. No, it says, what's the C at which the average value is made? So now you have to find the C. How do I find the C? Do I do it analytically, like find the solution to 7 plus sine of 2c equals 7 point, I guess I could do this analytically. Would you do this analytically or would you do this graph? Okay, so if you say analytically, again, I love your attitude, but you're going to probably have some issues. Because here's what. When you solve this analytically, sine of 2c equals 0.5471, right? And so 2c is the inverse sine of 0.5471. And then you divide that by 2. So c is the inverse sine of 0.5471 divided by 2, okay? All right, so inverse sine of 0.5471. Inverse sine of 0.5471. Divide that by 2. 0.289, yes? Boom, there it is. There's your answer, right? You failed. In fact, I could have told you without even doing this problem. Now, that's not even freaking possible because the question says C must be on 7 to 8. I don't even need to do the problem and know that's not possible. That cannot happen. Now, the problem you're dealing with is that the calculator, when you do inverse sine, is programmed to look in a very limited range. Whereas we know that sine actually could hit any value a million different places, and they're asking you to look over there. So if they give you a funky region, it's best not to do this analytically. You best do this graphically. Okay? Or if you wanted to, you could add, I don't even know if adding, what's the period of this? Period is pi. So you could try adding pi, adding 2 pi, adding 3 pi till you get there. But that to me is dangerous. Instead, you should instead go graphically. Graph sine 7 plus sine of 2x and graph 7.5471. Graph 7 plus sine of 2x. And what did I say else to graph? 0.5471? 471. I would also change my window to 7 to 8 so I look in the correct region. And maybe, I don't even know, maybe I'm going to go negative or 0 to 10 here or something like that so I see it. Okay. Oops. What the heck? Oh, 7 point is what I should have graphed, right? No, sorry. 7. That would intersect. I was stupid. All right. So I see only one possible solution. Boom. Intersect. There it is. 7 point. Now the only other question is, what do I report, the x or the y? And if it's find the c, find the x. And the answer is 7.564. Are you with me? Okay. So that's got a lot of gotchas to it. A lot of gotchas. Okay. One more, and then I'm good. Let's talk about a free response. Common question here. So, is this, I changed my notes on this. Is this where you're at? Yeah. Okay, cool. All right. Given the number of problems a student has to do at any time t, given this function, right? N represents a number of problems that he has to do as a function of time. Okay, whatever. I kind of made this up on the fly. We'll see how it goes. Find and interpret n sub 8. If you find n sub 8, I don't have to take a derivative. I just plug and shove. So 13 plus 2 sine of 4 pi. What does that equal to? 13. Would you please interpret what that means? I know you don't have units, so bypass units. What does that mean? At time equal 8, the student has 13 problems to do. Perhaps this is fluctuating because he's doing problems or she's doing problems. While I add problems, it's going up. I don't know. Whatever. Find and interpret n prime. What is n prime equal to? We got, what is n prime? What is the derivative? 2 cosine pi over 2t times the inside derivative pi over 2 evaluated at 8, yeah? So that is 2 cosine of 4 pi times pi over 2, or 2 pi. You with me? All right? Interpret that. N prime. Now, this I remind, if you remember, sometimes it helps to rewrite n prime as Leibniz notation because derivatives are rates, and that helps you think of it as a rate. At time equal 8, what's going on? The number of problems is increasing. Beautiful. A derivative implies increasing or decreasing. The number of problems is increasing at a rate of 2 pi problems per time unit, whatever that is. I should have given you units. You with me? Okay. Last but not least, find and interpret 1/4 of the integral from 2 to 6. What's that about? Okay, let me help you. 1/4 I could think of as this. What does it mean? It's the average number of problems he has to do on what interval? 2 to 6. This represents the average number of problems to do on the time interval 2 to 6, excuse me, 2 to 6, whatever the units are. Very common that you interpret an average value on the AP test. Okay, we'll practice that tomorrow. We'll do an AP practice fun sheet tomorrow. Okay, that's that. How did last night's homework go? Did it go swimmingly? It was an exercise in joy. Let's see. I feel like I made some changes here, so I don't know if this is just like what I had last year. Is this the same? Nope, different. Oh, I didn't have a back that I was supposed to look at. Oh, I'm so confused. Why do I confuse myself? Do you have two things? A pink and a white. How did the pink go? Well, not so good. Okay. Yeah, that Newton's law of cooling is good stuff. You physics people probably killed that. Am I right? All right. Maybe not. Okay. Let's post this in and go over it. And we might finish going over it tomorrow, actually. I just want to do it well. Tomorrow's not a new day. We'll do. Okay. Let's do this part. Just check the answers. What'd you get for 1 and 4's answers, please? E and C? B and C? Did you say E and C or B and C? B and C. Kylie's got the guts to put herself out there. Do you agree? Yes. All right, that a kid. B is in boy, and C. Are we cool? Yes. Okay, let's go to Newton's law of cooling. Cake is taken out of a 400-degree oven to cool in a 70-degree room. When will the cake cool the fastest? Now, assume when you get the cake out of the oven, the cake's temperature is 400 degrees. It comes out of a 400-degree oven. It's at 400 degrees. It's going to cool because it's being placed in a 70-degree oven. So when did you say it'll cool the fastest? Right at the start. It cools fastest, okay? If you were to sketch a graph here of temperature, capital T, maybe I should use that for Fahrenheit or something, sorry about that. But it's going to start at a temperature of 400 at time 0 and decay towards 70 degrees, which is an asymptote. That's one reason you learn rational functions, because, shoot, Newton's law of cooling has an asymptote. Do you agree with me there? Yes. All right, C was hard. You might not have quite understood what I was getting at here, but this, when you go to truly understand differential equations, you need to kind of have a feel for not just the equation, but also the differential equation and why it does what it does, all right? So imagine this, okay, T, capital T stands for temperature, little t stands for time. So this is the rate at which the temperature of the cake is changing with time, yeah? K is a constant that goes to the material in what's cooling. K is different for a cake than it is for something that retains heat. K is relative to the object. T is the temperature of the cake, and 70 degrees, T sub A is the ambient temperature of the room. It's the room's temperature. You with me? All right, then, here we go. Let's talk about how this and this go perfectly hand in hand. At time 0, or early, at time 0, let's talk about the temperature of the cake. At time, little time equals 0, what's the temperature of the cake? 400, right? Now, think about then how that affects the rate of change. If temperature is 400, then this difference is really large, yay? T minus 70 is large. Now, if that's large, then it must be the case that the derivative, or the rate of change, is large. So the rate of change is large. And if the derivative is large, that means the slope is steep. And isn't that exactly what's going on in this stuff? It's decaying the fastest thing. And that's because the differential equation would make it so. You with me? All right. Now let's talk about the other end. As time moves on towards infinity, what does the temperature of the cake approach? 70. The temperature of the cake starts to get closer and closer to the temperature of the room, right? Now let's then talk about the effect on the differential equation. If t approaches 70, then what does t minus 70 approach? 0. That approaches 0. That means the rate of change approaches 0, so the slope approaches 0. Isn't that exactly what's going on there? It's getting flatter and flatter. You follow? All right, cool. Without finding k first, is it positive or negative? K must be, why must k be negative? Tell me, in terms of the differential equation, is the rate of change positive or negative? The slope is negative. The only way that's going to be negative is if this is negative or that's negative. Now, can this, in the parentheses, be negative? It cannot. Why not? Because the temperature of the cake is more than the temperature of the room. This is positive. So it must be K.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All students, please come out and support the Boys Women's Ag Team on Thursday, February 28th at Chick-fil-A at Bellevue Shores, 6260 South Wadsworth Boulevard from 4 to 8 p.m.
Don't forget, there's still time to donate to the Wish Week campaign for 3-year-old Alex. You have until February 28th. Please don't get financial.
Okay.
The University of Colorado at Colorado Springs will be in counseling today to admitted students who are inquiring about their next steps. And juniors and sophomores want to know more about CCCS. Make sure you stop by counseling and sign the college visit book and sign up on the 7-hour app.
You are invited to Sycamology, hosted by Baylor University, Mrs. Weber's alma mater. United Sunday, March 10th at 2 p.m. in Carter. The casual event offers a closer look at the academic and personal growth.
Careful with your teeth.
The evening will end with a favorite Baylor tradition, Dr. Pepper Hour.
How'd that go? You with me? Bad? You didn't separate well?
Curry ball on Saturday, March 9th at 7 o'clock. This black hair will be jazz themed, so just for the 1920s. Bring a mask and tickets will be $10.
It said Club 278.
Will be offered Wednesday, February 27th, Tuesday, March 5th,
That's right there.
Thursday, March 7th. There will be a paper sign up for Mr. White's room, so come and learn some new moves for the ball.
First thing to do.
You know you have 20 school days left. You have a few details to finish off before
So,
Have you picked up your senior chalkboard and calculators? Have you paid your transcript fee? Fill out the team destination form? Turn in a copy of all your
let's use the initial conditions.
and apply for the DES scholarship? Stop by counseling if confused about any of these items.
Thinking about joining the GHS cheer team but want to meet the girls first? Or simply want to get into shape to train your flexibility and strength like a cheerleader?
Oh, there's actually two initial
We'll have
conditions,
open
right?
training for anyone wanting to come. From 3 to 4:15 every Monday, meeting
Let's first use
contact Carson Paul in the morning.
Today, if your last name is Medina Doyle, please come to the auditorium during cell hour. Tomorrow, last name is Daisy.
There are flyers in the office for middle school tennis, which starts on Monday, April 1st. Practices will be at various locations throughout the week, with matches on Saturday. We will all help with the experience, so beginners are welcome. That's all your announcements. Have a great day.
Now, I would wait later to find the K. You can use this to find K. You could do that in a lot of places, but I waited till later. I don't know about you. Are you with me? You're not with me?
No, this is I got LM 3:30.
3:30. I'll check it tomorrow first. Do you have it done? That's some noticeable signs. You got 3:30. So, okay, so here to find the C, you could go two things. You have at time 0, temperature is 400, which you might have overlooked, and at time 40, temperature is 330.
Yeah, I did the 0.
You did use it? Oh, perfect. This one's the one you want to use first because it drops this guy out. And it makes C clean.
But how do you, don't you have to plug 400 into IT?
For capital T, got yes. I plugged in 0 for T. Yep, you're right. Sorry, I screwed up. So this should be logged with 330, yes?
Yeah.
Okay, sorry, I totally messed up the other picture. 330. So this was 330. Now are we, sorry, I screwed up. Are we on the same page?
Yeah.
Alright, now the other one you could probably, I would probably use this one later. You can keep this one, go over it tomorrow first thing. Oh yeah, should we turn in the light sheet?
No. For extra credit.
Extra credit, come on.
Yeah.
Oh,
Much.
whatever, okay, turn in the light sheet, if it's done, I'll give you a couple extra
Yeah.
credit. Let's see what you got.